maybe at this point, yes, we can start recording. Thank you, Stelia. So, okay, so first of all, how to write an n-dimensional array. How to loop over an n-dimensional array. There are multiple ways. Let's start from exercise 1. How to use the other way around. So if someone you tried it, I think you may have started putting if conditions on the border. So if x is smaller than 0, then this should happen. If x is bigger than capital X, then this should happen, etc. Is that what you did? So my solution here is somehow cheating, I have to say. And my solution for this exercise is actually to use another NumPy function that, let me find, sorry, a second. Another NumPy function that will extend our size. So we'll extend our array. So something we can do is this one. I put it after exercise 1. So we can Laplace modes. So this we have the mode. For me, the best way to do this, even if you wanted to implement it with if conditions, was not to have the if condition at this level, but to extend the input array with a pad around. So in this way, we are extending the array with +1 and -1 at the beginning and the end. So the pad is basically doing this. So if I take a random array, just a second, let me take a random array of size 10. What you will see is that if I assign the shape and I pad it with mode equal wrap, this is basically going to create an array but no, not wrap. It's creating an array where I've added +1 to all the directions. Sorry, this is, I've added +1 to the size. So now it's an array of dimension 12 times 12. So let's do it for a range so it's easier to understand. So if I say a range just 10 numbers, this function is basically going to add one before, one after site. So this is inside our the content of our array, and we are adding one before, one after. So basically, we are creating an auxiliary array that has the information about the previous array plus the extra points. All right. And what we want to do now then, this function pad from NumPy supports already the various modes. And so if I put here reflect, for instance, we will see that this has been reflected, and so now it added 1 and 8. So this, if you want, you can you could do it by manually with some if conditions, so assign the values of this array manually, or directly use the padding function. But in general, this will be the approach I will follow, and I will not add inside here I will not add inside here the if condition inside the for loop. Okay, so then if now I want to fix, so now we have this extended array. If now I want to use it, can someone tell me what I should do? So you remember that it's one more. So out is going to have the same shape of the input array. I'm going to use extend here, but what do I need to change in this line? Can someone please help me here? Any volunteer?
The modulo operation, because it's padded. So
yeah, what do you need to do? Remove the modulo operation?
yes.
So yes, I need to remove the modulo operation. Perfect. Now, so I will remove all the modulo operation. Then the capital X, capital Y, I didn't assign it yet. Should I take it from what? Panayota, do you want to continue?
I would say the padded version.
If I take it from the padded version,
I know you'll have problems again now.
It's the same, either padded or no. If I take it from, I will take it as well from the padded with a change though, because padded is bigger than out. So if I take it with the padded, like I do this, we are going to run in error because we are trying to go bigger in out since we are going to 12 and we cannot. So the range will go from 0 to 12, but this is up to 10, suppose. So I will take it from the padded with the change though of using at this level here a range that is suitable or better. Yeah, let's take it from the padded and I will group from 1 to x minus 1, so the inner values. Okay, but also in the out now I need to subtract 1 because this starts from 1, the point 1 of the external, it's everything is shifted of 1, and so here I subtract also 1. Or do you all agree with this choice? There are other ways to do it, but now this is padded, and so I'm writing on an out that is the same size of the input, and so I will do this. Do you see any mistake? Shall we try it out? So let's try it out this mode, and let's use let's compare it. So I will do Laplace modes with image Laplace, and then here I say mode is equal wrap as well. Okay, and so finger crossed, everything should run. No, it didn't run. What is happened? What happened now? Maybe there are zeros. Is this running first place? So do you, any one of you see problems with the implementation? It's not returning out. Yeah, that's an issue. Okay, this now seems fine. So it's true with the mode wrap. Okay. Sorry, yes. And if I try reflect now, still finger crossed, it's not working anymore. Why? Where it should work again, I need to, well, we will try again why it's, we will try to understand. Anyone sees an issue with this? It should work Laplace mode. It should also work, just, yeah, let's continue and then we try to figure it out, unless someone sees a mistake. Did someone else try another approach? Okay, this was a bit cheating, like I said. Did someone else try another approach? No? So maybe let's go, since the time is running very fast, let's go directly to exercise 3. That is the one, it's more the most generic implementation. And my way to do the NumPy Laplace an n dimension. So here I'm going to implement now an n dimension NumPy Laplace using MP-roll. And this, I will do it with this function here. So again, I have the array, I get its shape, okay? I get the number of dimensions. no, that's not okay. I get the number of dimensions. Why do I get the number of dimensions? Because the output, if you check the math, this is something maybe I didn't tell you before. But if you try the n-dimensional, these approach here are 4 terms and is a -4. When we go to 3 dimensions, we will also loop around, do the difference along z, for instance, add a z everywhere. And this difference, the subtraction, if you define it, if it's discretized the equation, it's not going to be -4, but it's going to be -6, okay? So that one here, I need the number of dimension because it's 2 times n times the array, the constant term that we are adding here, this part here. It's now a full array. Okay, so the output, instead of instantiating, so let's compare, sorry, one by one with this one. Otherwise, so the output before I was instantiated to 0 and assigning in the loop. If now we remove this restriction of doing the loop where we want to do it directly, all of it in one iteration, so with the global, with the volume operations, I can start assigning the output to be -2 times n times array. So this is the array, and I'm doing this operation here. So it's a copy multiplied by -2 times n. And then if I want to add the difference per direction, I'm using the roll function of NumPy. So the roll function, what does it do? The roll function, it's rolling. If I take a range, sorry, I need to put the shift. If I take a range and a shift of 1, instead of being 0 to 9, now it has been everything rolled of 1. So it pushed after a shift of 2, it becomes 8, 9, and then the rest. So this is basically doing a shift of our operations. So here I'm rolling the array, the extended array in this case, of 1 and -1. So forward, rolling forward and backward. All right. On a specific direction, so the axis will tell us on which direction to do the rolling. All right, so this is saying which of these index needs to be rolled. And then with inner, I'm going to take the inner shape. So out is still the out is still the dimension of the array, while extended is extended of 1. And so like before, like here, I'm looping in 1 - 1. Now instead rolling, I roll the full volume for then taking the inner shape. And I add it to out. So I'm doing plus equal to out. Other question on this approach? So this is how we would implement it, a general approach, an n-dimensional array with NumPy. Questions? Sorry, Nicholas. Yeah, Nicholas. By the way, yeah, I didn't see your comment on Slack. Did you try the approach that what I explained above? So do you use Linux?
Yeah, just joined. I connected to the cluster, but I don't know the command to open the Jupyter notebook.
Okay, so you connected the cluster with the port forwarding as described above with 8891, etc., right?
Yeah.
And then you just press this, the URL that I've given here, this one, and will open in your browser locally. You don't need to do something else. So if you hit just the URL, it will open, you should open this one in your browser. Okay, and then what I explained before is that there is the main that it's me. You can create your own notebook to work on. Don't change the main. And you can reload it when I will save it, and then you can reload it by pressing reload notebook from disk and to update it. So that is the instructions. Now your question instead is actually good if the roll function is computationally expensive for large arrays. Yeah, it is a copy, so it's as much expensive as a copy plus the additional cost of shifting. So it's significantly expensive. Would be cheaper to do this operation. So if you were writing something in C, you will never go with a roll function. You will never create first a rolled version of the array for then accessing the neighbor, but you will directly access the neighbors. So this is a very good question. Though in Python, there are no way to do this in NumPy. So you cannot create a shift. The way to create a shifted view of the array, yeah, you can create a shifted view of the array, or you do a copy like this, but they're both not so efficient. So
okay, thanks.
So this is a level NumPy. Later we will see how to go over this roll function, but this is how I would implement it with pure NumPy. Other questions? Okay, so if there are no other questions, I mean, now I want to show you. So this is the general. So I hope it's clear, the implementation. And now just to, again, to check it, if I compare it with a 3-dimensional array with the wrap, again, we get true. So they are all similar to each other. Okay, so we are doing the same thing. If now I want to compare the performance, so above we have run this notebook, we started the timing and we have run this one. So we got this result. If now I want to check the performance, sorry, I will do the same. And so I will loop over the size, create a random array, and append a new instruction that is NumPy, and just running this NumPy class and just check the comparison. Sorry, now this is old. Why did I go there? Sorry, shouldn't be that one. That it's something else. Where is my Laplace operator? This is defined. And if now I run this one, we should get the previous plot in memory. So the times has been replaced by something above. So we have this one now. And if I go here, what do we see is actually that even if now we use this more expensive operation, actually we are performing as well as the implementation in SciPy that we were using before, so the blue line, telling us that probably SciPy did similar choices to me in their implementation, and the main difference is mostly in the initialization cost, where probably they're not using maybe the padding like I'm doing here. Maybe they're doing something else. But the computation intensive component is actually very similar, and we're performing in a similar way. So I would say that SciPy did did a similar approach. Now, what can we do to improve our function? So unless there are questions, no. So what can we do for improving our function? Well, let's first check what is the most computationally expensive demanding component, and which is going to be the roll, like Nicola suggested. And we can check this by using the profiling function of Python. So cprofile is a built-in profiler for Python. Sorry, someone is changing the notebook. Please don't do that. Don't run the notebook, this one. So cprofile is the profiler of Python, and we can use it to profile an instruction and check what are the costs of this. So basically, we profile every instruction that we have inside the function, and will tell us the cost. So here I'm defining the array of a given size, and then with cprofile, I run it, and I want to sort it by the total time of this. So let's run it, and this is the kind of output we get. It's a bit confusing at the beginning, but if you look at it once, it will tell you everything. So it's divided by function. So these are the functions we have. We are calling inside there. There are many. And it's ordered by cost. So the total time of the NumPy array is 35, in this case, milliseconds. Okay, which has been called once. So the cost per call is equal to that one. The cost of the function is 35 milliseconds, and the second most expensive component is the rolling part, which takes 33 milliseconds. okay, which has been called 4 times, and so we have the cost, it's 8 milliseconds per call. So this is the most expensive component, the roll. The other quite expensive component is then the array pad, which is an initialization cost. And so this is 9 milliseconds. If you sum up these two, actually it give us more than the total cost, telling us that the profiling function is not 100% accurate, because what it's actually doing, it's running the function multiple times, measuring during this run several components of it. So these may not match between may not be done in the same run, etc. So it wants to be precise, but sometimes may not. Okay, though this is telling us what are the most expensive costs. Then the rest are all the other internal calls that are made, but we don't care about that, just about the first. So what we want to improve is the first. Okay, so this is what we have learned by using NumPy. So NumPy is almost performing as well as SciPy, so they do similar things, but it's not optimal. Question about profiling, etc. Okay, if there are no questions, now we go to the I don't know if now, I hope that so far it was clear, and you don't have too many questions about the notation I used, etc. So if you did some work in Python, this should be quite standard. But yeah, I know that sometimes I do some advanced stuff like this one. But yeah, if you have questions, please ask me. Or I suppose, I mean, I don't have problems to explain also basic concept of Python. Just please ask for it. Otherwise, I proceed. Okay. So now let's go to let's give up, leave behind all the NumPy part, and let's go to something that really helps you to gain performance out of the machine. And so let's start with the topic that I wanted to cover the first hour, but as usual, I'm too optimistic. And this topic is Numba. So Numba, which documentation you can find it here, documentation. It's a very nice tool, very, very nice, for, like they define it in their manual. It's used, okay, this is directly the manual, maybe on their own page is nicer, the message, but it's used to produce HPC code in Python with just-in-time compilation. So what Numba offers you is this JIT command that is explained here, JIT, where JIT means just in time. So this is a just-in-time compiler, which means it's not compiling overhead, but it's compiling at the first time you call the function for the arguments you gave. So what you will do in a normal C code like you did yesterday, usually when you define a function, you need to explicitly say what are the types of the argument. So and in this way, the compiler can optimize the code. If the compiler will not ask you for the type and would be any type, then that will be a very slow code. And this is also one of the reasons why Python is slow, because it's supporting any kind of variable. Though that's the reason why Numba is using a just-in-time compiler, because at the moment you call the function, it will learn what is the type of the X and Y of the input you're giving. And if it's integer, complex, or float, will compile a dedicated function for it. So there is an overhead, a first overhead that is due to the first compilation, but after it has been compiled once, it will use always that one. So that's what Numba does. Then you can also specify inputs, and then we'll do some casting. That's something else. So suppose you want to use, by default, Python use long type. So 1, it's always an integer 64. But if you want to use, to compile it for integer 32, you can do this by specifying here. So then Numba will cast for you 1 to integer or to float or to whatever you say to compile for it. Okay, Numba, it has a very nice documentation. So later you could, it would be nice if you have a look at it and then maybe ask questions. So, but now what do? We want, the idea is it's as simple as this one. From Numba import JIT, okay? And then we define a function like this one. And then we call f of 1, 2. And this is going to compile it and run. If you saw, it took some time the first run, but the second, it's immediate. Okay, this is it should be as simple as that. Okay, now what we can do then is to take our first Laplace, this one, and compile it. So we compile it with just saying JIT. And we get a Laplace. Yeah. Sorry.
We always have to put JIT right above the function.
Yeah, now I'm going to explain that. Yes, okay. You should put it just above the function. So now I'm going to explain a couple of things. So what happened now? This is now a CPU dispatcher, blah, blah, of the function Laplace. If you would have run it without JIT, so this is a small parenthesis that I'm going to open, Laplace will be a function that is being defined here. Okay, so you obtain 2 different objects Laplace. How this is done? This JIT here, it's what is named in the Python jargon a decorator. Okay, for those that are not familiar with decorators, they never use them, I will give a short explanation now. So the decorators is something that is defined in this way. So this is a wrapper usually. This is a wrapper. I define a function that I name FNC, which for instance takes a value A and returns it, return A. Okay. If now I execute it, it will tell me wrapper is not defined. So there is no anywhere a wrapper defined. Because this decorator, what actually Python wants is a function. So like JIT, what is it? It's a function. It's a function that when you put a net in front will act as a decorator. What are the specifications of a decorator? The decorator, this wrapper, is something that takes a function. Okay, this is a decorator. And the most trivial thing you can do is to return the function itself. Okay, so basically it's something that when we define this function, instead of being directly defined, so when we do this instruction, Python will define FNC as a function. Okay, like this. If we make it go to the decorator, instead, we still get a function FNC that you say, okay, there is no difference. Yeah, there is no difference because we return it actually the same. The decorator is actually returning that. So, well, what did we do now? So, but I'm going to explain better what is the concept behind this decorator. But the main purpose of this decorator is to absorb the function, okay, and return a function. Here we can return completely something else. We can return print, for instance, the function print, and Python will not realize. So when I instruct this one, FNC now it's actually the function print. We completely forgot about this function here. And if I call now FNC, instead of getting the value, it will print it. So if I say 2, this is now a print instruction. It's going to call print because to function has been assigned the value print. Okay. But where usually these decorators are used is, for instance, to wrap, this is why I name it wrapper, is to wrap the function with some additional instructions. So what someone usually will do is to have inside the decorator another definition of a function. So you can nest inside the decorator a function. So this is a decorated function. okay, that takes an argument a, which is the same of the function. So this is decorated. And basically, let's do something like print a, and then we return fnc of a. And here we return the decorated function. Do you see what this is doing? So we're getting a function. We define another function that takes the same arguments. We are printing the argument, and then we return the result of the previous function with this given argument. Does it make sense? So if now we run, we wrap it again. Sorry, I need to redefine the decorator. We wrap it again. Okay, this is now this decorated. The function is this decorated here. Can someone tell me what will happen when I say a equal fnc of 2? What will it happen now if I run it? Anybody?
I think that a will be assigned the value 2, and then the value 2 will be printed as well.
Perfect, thank you. So this is what we see. The 2 here, it's the printed, so it's going here. So it's high, it's going to go through that instruction, that one. And a, it has also got the value 2 because the function is just returning a. Okay. Let's try again to do an exercise. Can anyone write a decorator that times a function? So the idea is to start a timer here. Here you want to start it. Then you want to call a function a, assign the value, the output here in a variable. Stop the timer, print timer value, and then return out. Okay, so just fill up these gaps here. Basically, and you need to find out to time things in Python. So this is a decorator that, for instance, will be a timer. Every time we call this function, this is somehow a useful decorator, will time it for us, still behave like the function, so returns the function, but in the meanwhile, it time the execution. So we start the time here, we stop it here, and in this way we've timed the execution, and then we return the output. Okay, I give you 5 minutes maximum to do it. And if you have a question, please ask. Okay. Can someone tell me what should I do? I mean, I put more instructions here, so basically at the moment we need what function to put here in start and stop. What are your suggestions? Wait, there was also a question. Sorry a second. Dimitris Dimitris is asking me if I have some problem with putty. Is anyone using putty here that has been able to connect in general? So from Windows.
Yes, I'm connected.
Okay, thank you, Valeria. So the instruction I gave before worked fine. So maybe it's just a mistake from your side. Sorry, just a second. Sorry for that. So yeah, Dimitris, I think there was the L in front of 8891. Okay, you sort it out. Perfect. Now, yes, someone tell me what I can do here. I saw before there was an unmuted microphone.
Yeah, can get the current time from datetime now function.
So from date time. Okay, so you say from date time import. Which one did you use?
From datetime import now.
Okay, I think also the time from time import time. If I call time, should give me in the
yeah, it's the same thing.
Millisecond. So suppose this one, and I call now. It's the same from the. Maybe I don't need to say this time. No.
I imported just datetime and then I use datetime.now.
Okay. Okay, this is a datetime class. So this is a class. Yeah. Okay, let's go instead with a float number, that is this one. So this is time in second. Also your it should have worked. So if I do use this one and I get this time in second, I can then say I call time when I start, I call time when I stop, and then the elapsed time is stop minus start. This is the elapsed time in second. Okay, so this is a function named timer, and if I run it now, what do we expect? We expect to print the elapsed time, and this is how much it took. Order of microsecond, 0.4 microseconds. So you can use the unit measure you prefer for printing it out better. So this is, for instance, a very useful decorator that would allow you to decorate functions for getting the time. Can I say that decorates any function? I mean, if now I want to decorate, suppose I want to decorate the print function. So a way to decorate something is either with the at, okay? But like I explained to you before, this is just, the at is just calling this function. So I can just say timer of print, and this is tprint. This is doing the same thing as decorating a function. So we call timer with the function print. Print is going through this, defining a decorated version, and I get tprint. Okay. This is a decorated function. So the elapsed time now, it's this is tprint is printing time, is the timing print, the print function. So if I say tprint of I should get I plus the elapsed time of it. All right. But can does it actually work for any print? So if I say print 1, 2, this is printing 1 and 2. If I say I, 2, what is going to happen? It will not work. Why? Because the function decorated takes one argument, and so it's expecting the function to take one argument. So how do we define then a general decorator that takes any kind of argument? If you're familiar with this kind of problems in Python, the solution is to use star args, star quarks, and pass the same arguments to function. And in this way, this is a general decorator. If you're familiar with it, you may know what is star args, star quarks. Otherwise, I can. So this is the tprint now will work with any argument because it's unpacking the argument. So this is how to give a general set of arguments. If you're not familiar with it, the time is passing very, very fast. So I will not do another parenthesis on this. Let me leave it for later. But this is how you will define a general timer. Ask me later in the break, please. Okay, or better, at the beginning of the lunch break, I will explain that part. Remind me. Now let's go again. This was another big parenthesis. Let's go in the JIT. So JIT here now JIT is decorating Laplace. We do it like this, and it's producing a Laplace function that will be compiled at runtime. Okay, so this decorated function now we can simply call Laplace, and again let's check for compatibility, and then let's check the time of it. So I check for compatibility, and here I'm calling, wait a second, let me clean up some stuff because here this is too much. So this, let me put it after, or let's remove it. This is a parenthesis on the decorator, I keep it there. Let's remove everything from here. Let's remove this one, I will do it again below. So this is the Laplace function that we defined before. Now let's define a first numba Laplace as the decorated JIT of Laplace. Okay, like I showed you before, it's the same thing as decorating it. So this is Laplace, this is the numba Laplace. Okay, let's check now with this numba Laplace that works. So we still have a two-dimensional array, and this is working. So here we have compiled it. And now let's check its performance. So let's do the same that we did before here, but for numba. So we replace numpy with numba, and we're calling numba Laplace, and we plot it. Okay, we are faster. Nice, look at it. It's this was the Python. So numba what did took this Python and moved it there. Okay, do you appreciate here that we are significantly faster? We are not, we use a log scale. So now I'm going to remove the log scale, but we are significantly faster. Okay, an order of magnitude is almost faster. So you cannot though appreciate too much now how much faster we are with numba. So this is great. I mean, you write your simple Python function, you just add JIT, and you get a compiled function that is times way faster than the other. Okay, so you cannot appreciate how faster we are though at the moment, how many factors, because we are in log scale, and we are using the log scale only for the reason that if I plot it without log scale now these times, if I plot it without the log scale on the y-axis, well, what happens? You still understand nothing, because this is the cost of Python, and this is the cost of the rest. So as first, let's drop behind all the pure Python stuff, and let's compare only SciPy, NumPy, and Numba. So I start from 0, and I'm using only these 4. Okay. Now I run it and computing the timing, and what I get is this plot. So SciPy is here. NumPy was faster than SciPy. So before you couldn't tell this, but it's actually faster. It's 10% faster. And Numba is a factor of more than 5 faster than SciPy. Okay, it's here. But still you cannot appreciate something well. And if I go back, here you cannot appreciate the difference. And if I go back to logarithmic scale, again, you cannot appreciate the difference neither, because then you are in a more difficult logarithmic scale, and it's difficult to say what is the factor from year to year. Okay, so they're both difficult. What is the way to try to appreciate this difference in numbers? To appreciate these different numbers, the way to do it is to actually plot not the time, but the performance. So the performance is defined somehow as the inverse of the time times the numerical cost of it. So in our case, we are running this problem for an array that has size times size. So our loop is going over both x and y, so over both sizes. So the numerical cost of it, it's size times size, so it's size square that I access from the list of indexes. So I take the list of indexes, I multiply by square. So this is the list, the values that we are running over squared. So we are running over 2 to the power 13. This is squared. I take the list of indexes, I divide by the time, and I get I apply this to get the performance, and this is going to show us the performance. So basically, these are the number of sites squared, of volume square, that we can do per second. And now this is, again, a linear scale, not logarithmic, where you can appreciate this difference at least on a longer range than here. So you can see that we can appreciate the difference here. From this one, that is Numba, now higher is better. Before lower was better, now higher is better. So we can do much more work per second. And the other two are performing similarly in this region here. Okay. Now, just a few comments, then I let you ask questions. What do we notice from this graph? Again, we notice a flat region somehow here, then it's dropping. I will explain you later why. We notice a flat region here somehow, and a region which has zero performance at the beginning. So zero performance, then we reach peak performance, etc. Okay, we have zero performance because it's not actually zero, it's just the scale again that is not logarithmic. So if I put it again in logarithmic scale, so I say log y equal true, now I get, you see there is a difference also in this region. But again, it's a matter of which one you're interested more. And in which one are we interested more? In this. Why are we interested in this one? Because this one here, it's the peak performance of our code. So this is the sustained performance. But this is actually the actual what we need to look at when we are doing HPC, because we suppose that the size of our array, of our thing that we want to analyze, is big. It's not small. We use HPC for big numbers, not for things that take order of milliseconds. We want to do it for things that take sort of seconds. And so we want to use these functions for big arrays. And what we are interested in is in this region where there is the sustained performance, and not the actual performance at the low region that is mostly domained by what? By overheads. So again, like here it was flat, these are overheads. This is the linear increasement in performance that you see when you are actually doing computations, there are only constant costs. So if you want to define this function, to fit this function, it's a constant plus a linear increasement with the volume. So this is C plus something to the power of something coefficient. You can write it. It's the cost, the time, it's equal a constant plus slope b times the x to a certain power c, where now the certain power c, it's not 1 because, x to the power c, where the power c at the moment is not 1, but actually 2, because our cost is growing with the size squared, not with a single size. X is the size, and our cost is growing with the size squared. So if you want to fit this function, a first fit you will do is this one, and you will find overheads, C equal overheads, sorry. And B is equal performance that you get by doing time divided by cost. Okay, well, anyway. Okay, so let's do it like this and put text. Anyway, leave it like that. It's fine for now. So these, so we are interested in this region. This is the HPC region. This is overheads. We are not interested in it. And we can say that number is how many times faster than the implementation? 2 times 0.5 faster. So we are lucky that here it's 1. So this is directed 2.5 times faster. Question about this? I don't see questions around. So
only one.
Yeah,
sorry.
Please, thank you.
What about, because I see number decreasing then, what about larger values? Or we just care for the high performance now?
No, that's actually even more high performance. It's just something expected that it will be shown even more later on. So if now I actually run it more, I run 14, that I know it takes some time. So if as more as I try to increase the size, it will take time because I'm timing 3 and only 1 it's significantly faster. So I will drop it after. Let's wait a second to have it run. But the main reason why you see this is because you are requiring data access, and if you know the specifications of your CPU and in general how the performance is affected by your hardware, what you actually expect. So now it has run. It's a decrease in performance that you always expect, and then a flat region again, like you see here. So it has been quite nice. Where this second flat region is due to a change in the bandwidth that your data can be accessed to. So later we will see it back in another example that exploits this even more. But basically you have a region now here where you have your CPU has an internal memory that is named cache. So it has different sizes. There is the L1, L2, and L3 cache. And your CPU is, in this region, it can actually fit all the data that your array has, the size of your array, inside this cache. So it can copy it inside it and have a faster access to the data. So there is a higher bandwidth here. After that, the data do not fit anymore in cache, so this needs to be accessed from the memory, from the DRAM, where they are staying in, and then this is affecting your performance in a way that you are seeing here the bandwidth of data access from the DRAM. So thank you for this question. I wanted to explain it after, but I may have forgot.
Sorry, I forgot what
Yeah,
I was going to ask. Okay, if I remember, I will ask that.
No problem. Other questions?
Yeah, I remember.
Perfect. Thank you, Jonas.
So when we are using pure Python, do we use the cache memory, or do we do not use it at all?
That's another good question. I mean, for sure you would, but you are significantly slower in the operation itself.
Yes.
So this operation, when they are basically, this was, I think, explained also in the beginner workshop, that when you do there are two different ways of doing calculation. Either it's a compiled version. So when you compile your code, you actually translate your operation into machine instructions, so in machine code. And these are every operation. So here the addition that you are doing, the access, the additions and the access. These are actually all operations that are done in that are done directly when you compiled it. They are direct machine instructions. So it's actually take this number, add it to this number. Okay. Python instead, for doing this operation, is doing so much more work that really what you see here, it's not, you will never see the effects of the cache because you are not memory. So there are two kind of limitation in your calculation. One is computation bounded and another is memory bounded. So here your calculation are computation bounded, where you actually have much more work to do than the data you want to access. So adding two numbers results in so many instructions that the machine has to do that you will never see the effect of the communications. On the other side, instead here, the number of operations your machine has to do is optimal. And what you are limited then is from the bandwidth that you have from accessing the data. Okay.
Okay, thanks.
So if I do something that is an instruction that takes a lot of computation, like a sign, suppose a sign of X, doing the sign, it's an iterative procedure that requires a lot of computations, not accessing the memory. So when you give the number 1, it's getting the number 1, but then computing the sign, it's requiring a lot of instructions. So it's looping around in order to reach the sign as a certain precision. It's not something you can do exactly in one instruction. So you don't have on the hardware any circuit that computes the sign, but it's actually done iteratively with other methods. And so this is computation bounded again, because you have a lot of calculations to do. But then if you do it something like an addition instead, it's very trivial to be performed, and then that's communication bounded. Okay, we are very close to the lunch break, so I would be happy if there are other questions. Otherwise, I show you a couple of things more that anyway I will show after. Yeah, please, Panayota.
All the speed up is coming using JIT is coming from the fact that it kind of precompiles it.
Of course, exactly. Later we will see also what is the speed up by using pure C. But exactly, the speed up here, it's all due to the fact that we are pre-compiling and we are running on machine. So we are running these instructions. So wait, yeah, let me rephrase it better. All the speed up is due to the fact that we are pre-compiling and to the fact that why this NumPy is low. NumPy was low because it was creating a lot of copies. So NumPy was low because we are doing this rolling operation that we saw here. It's the most expensive. And basically, we are still, all our loop still lives in Python. So still lives in Python. It uses NumPy for volume operations, but it's doing copies of data. So it's doing a lot of calculation more than what would be needed, right? It's rolling, copying, creating a new array, adding it, etc., etc., etc. What we are doing now here instead, it's very optimal because we are not creating any copy. So actually, from the point of view of implementation, our original Python code was very optimal, but was slow because it was in Python. So it was optimal because we are direct accessing the data. Okay, for this reason, it's optimal. but it was done in Python. With JIT instead, this is going to be done at machine level, and this is how you would implement it in C anyway. And this is why it's much, much faster. Not because NumPy is slow, NumPy is also using C, and it's also optimal, but because the way we're using NumPy was suboptimal, okay? Because we're using for doing these rollings, etc. So we are using a suboptimal approach than what we are doing here. So if here I would do a copy, rolling, etc., that would be very expensive. But now that we compiled the simple way, so simpler is faster if done in C. Okay, that's the message here. And then, okay, so if there are no other questions, then I would close here this morning, and I'm significantly behind of my plan, but don't worry, we'll keep all the rest for an advanced training. So yeah, I was too optimistic. It took the 2 sessions for doing what is here. So now we'll shift after this. It should fit in one section. So later we will finish with Numba. There are a couple of things more, doing CPPYY in the next session here. And then we will see some MPI and leave CUDA and CuPy for another time for the advanced workshop.
Maybe we can sort out one day, a couple more hours or something. I don't know. Whenever.
Yeah, I mean, we can have a dedicated event also. It's not a problem, because in the advanced workshop, there is that we are going to have GPU programming. So I think it's also more suitable there. I just wanted today to give some clues here, but anyway, they didn't have an introduction to GPU, so maybe it's more suitable there for the advanced workshop. So
okay.
That's going better. I thought just I would be faster, and I wanted to show more.
What time are we scheduled to come back to this? Let me
1:45, because there is the seminar. So
yeah, okay.
It's the time I'm showing here.
So thank
sorry,
you so much.
Sorry, 1:15, not 2:01.
Yeah.
Sorry. Yeah.
Thank you for now.
Yeah, thank you all for joining, and I hope please, if you have questions during the lunch, ask me. I will be away now for some minutes, then I will be back. And yeah, just tell me, give me some feedback if I'm going too fast, too slow, etc. So then we fix it for after. Okay, thank you all, and see you back in 3/4.
Okay, thank you very much. Bye. For now.